Alright, silly people, here's the situation. We're going to be doing Fourier filtering again, but we're just going to filter the square wave, which is this function here, where these are the floor functions of 2 times t, and we're going to be making use of NumPy's version of the floor function to do that, right? But the process is pretty, easy if you did the last problem in the book. So we're gonna always just import our packages and then create the function. So def f of t is made to return if the floor of 2 times t is mod 2 is equal to 0. That means that the floor of 2 times t is even, and we can have it return 1. Otherwise, so else, you return -1. And then we wanted a n equals 1,000 elements like list, which represents one cycle of this. So let me create an input list that I'm just going to call TLS. That's going to be the lens space from 0 to 1 for a full cycle with 1,000 points. Create an output list called square to do the square wave, and then just run for t in TLS, append square with f of t, right? And then we can, plot it. So plot square, and you get back one full cycle of the square wave, right? So looks like a square, pretty nice. But then we're going to also Fourier transform it, truncate the values of the last 900 points, and then plot it again, and you'll see that it looks kind of weird. So I'm going to create a variable called c square, which is going to be the Fourier transform of square. Then we're going to take that list and make all but the first 10 values equal to 0, right? And then just plot that on the same plot. Or actually, first of all, after you do that, you make square smooth for the smooth version of this equal to the inverse Fourier transform of the Fourier coefficients, so c square. And then you plot square smooth on top of square, and you see that you get the square wave, but then also this smooth quote-unquote version of it, which is approximately the same as the square wave, except you get these wiggles. And those just come from, again, whenever you set all but the first 10 Fourier coefficients to 0, then you get rid of that higher frequency behavior. And so if you didn't get rid of those, you would see a really high frequency wave here that is very close to the line. And down here you'd see the same thing. But because you got rid of those higher frequencies by doing the Fourier filtering thing, you don't see those. You just see these low frequency waves. To illustrate that, I'll make it so that you only kill off the last 900 values. So you only keep the first 100 Fourier coefficients. In that case, yeah, these waves will have a higher frequency because you didn't cut off those higher frequency values. And if you wanted to not cut off any of the frequency values, then you'd get back the same thing. So yeah, that's Fourier filtering in a nutshell. All right.